Let's take a look at section 4.4, which is concavity and the second derivative test. We have already seen that locating intervals in which a function f increases or decreases helps to describe its graph. In this section, we will see how locating the intervals in which f prime increases or decreases can be used to determine where the graph of f is curving upward or curving downward. So let's suppose that f is differentiable on an open interval I. The graph of f is concave upward on I when f prime is increasing, and it's going to be concave downward on I when f prime is decreasing. If we look at the first graph, this would be an example of a graph that is concave upward. If I look, as we move from left to right, if I look at a series of the slopes of the tangent lines, as we move further to the right, we see that the tangent lines are getting steeper and steeper and steeper, which means that the slope are increasing, which means that f prime is increasing. And that's what creates this kind of cupped upward shape that we see. Another way to think of concavity, if I pick a point on the graph, on the intervals where the graph is concave up, the curve will always lie above its tangent lines. Conversely, if we look at the next graph, if I look at the slopes of the tangent lines at a sequence of points as I move from left to right, we see that the slopes of the tangent lines, i.e. the slope of the graph, is decreasing, which means that f prime is decreasing, and that shows that the graph is kind of cupped downwards or concave down on that interval. Whenever a graph is concave downward on an interval, what we will notice is that at every point in that interval, the curve will lie below its tangent lines. Theorem 4.7 gives us a test for concavity. Let f be a function whose second derivative exists on an open interval I. If f double prime of x is greater than 0 for all x in I, in other words, if the second derivative is positive, then the graph of f is concave upwards on the interval I. And this makes sense if we just go back a moment ago. If f prime is increasing, the function that will dictate whether f prime is increasing or decreasing would be its derivative, which is given by the second derivative. So when f double prime is greater than 0, that means that f prime itself is increasing, and therefore the graph would be concave upward on I. If f double prime of x is less than 0, meaning if f double prime is negative, then f prime itself would be decreasing, which means that the graph of f is going to be concave downward on I. Let's take a look at example 1. Let's determine the open intervals on which the graph of f of x is concave up or concave down. Throughout this chapter, if they're asking for concavity, we want to get to the point where we know that that's going to be synonymous with finding the second derivative. So we need the second derivative. Let's begin by finding f prime first. The derivative of e to the u is e to the u times u prime. So it's going to be e to the negative x squared divided by 2. From the chain rule, we need to multiply by the derivative of that exponent. The derivative of negative x squared divided by 2 is going to be negative x. So f prime of x is equal to negative x e to the negative x squared divided by 2. In order to find the second derivative, this is going to require the use of the product rule. We can think of f prime as the product of e to the negative x, as negative x times e to the negative x squared divided by 2. The derivative of the first function is going to be negative 1. Leave the second function alone. Now we leave the negative x alone, and we need to multiply that by the derivative of the second part, which is e to the negative x squared. Well, that's the same thing as the first derivative we just did, which is going to be negative x e to the negative x squared divided by 2. Let's go ahead and simplify this. We see that f double prime of x is equal to negative e to the negative x squared divided by 2 plus x squared e to the negative x squared divided by 2. And this would be our expression for the second derivative. Oftentimes it's going to be very convenient, especially if you have a function that's a product of an exponential times a polynomial or maybe an exponential times a trig, is to factor out that exponential, and I'm going to go ahead and do that. We can rewrite this as e to the negative x squared divided by 2 times the quantity negative 1 plus x squared. We now want to examine where the derivative is positive and negative, so we're going to do a sign chart for f double prime. And in order to do so, we first would want to find any places where f double prime of x would be equal to 0. That is, where is e to the negative x squared divided by 2 times negative 1 plus x squared equal to 0? This is already factored, so we can go ahead and set each factor equal to 0 independently. For the first part of this, e to the negative x squared divided by 2 equals to 0. Well, e is never going to be 0. The range of the exponential function is from 0, not included, to infinity. So this first part won't produce any solutions for us. However, over here, I can add 1 to both sides, and then take the square root, and we get 2 places where the second derivative is 0. Those would be positive and negative 1. We should also look for the places where potentially f double prime could be undefined. If I go back and look at the form of f double prime, it's an exponential times a polynomial. This exponential is going to be defined for all real numbers, as 2 with the polynomial, and therefore 2 will be the product of the two. So f double prime is going to be defined everywhere. There would be no places where our second derivative would be undefined. So altogether we get 2 numbers that we're going to use for our sign chart. Those 2 numbers are positive 1 and negative 1. Let's come over here. If I plot those 2 numbers on a number line, they're going to subdivide the number line into 3 regions. Region 1, region 2, and region 3. Let's pick a test point in the first region. In region 1, we could do something like, let's say x equals negative 2, and we want to investigate the sign of f double prime. F double prime of negative 2 would be equal to e to the negative of negative 2 squared over 2 times negative 1 plus negative 2 squared. F double prime of negative 2 is going to be equal to e to the negative 2, if we work the exponent out, times positive 3, which is simply 3 over e squared, which is greater than 0. So what we would know is that in the first region, f double prime is positive, which means there the graph would be concave up. Let's take a look and see what's going to happen in region 2. A good test point to use in region 2 would be x equals to 0. F double prime of 0 is going to be e to the negative 0 squared divided by 2 times negative 1 plus 0 squared. And this should be equal to negative 1, which of course is less than 0. So in region 2, f double prime is less than 0, which means that there the graph is going to be concave down. And we have one more region to check. Let's take a look at region 3. In region 3, we can use the test point x equals positive 2. F double prime of positive 2 is going to be e to the negative 2 squared divided by 2 times negative 1 plus 2 squared. If you work this all the way out, this is also going to end up being 3 over e squared, which is positive. So f double prime in region 3 is going to be positive, which means that the graph will be concave up. in region 3. So by doing a sign chart for our second derivative, we were able to determine the intervals of a concavity of f. Let's summarize. So whenever the question asks about where a graph is concave at, whether it's concave up or concave down, these should be intervals in its domain. The graph of f is going to be concave up over the interval -infinity to -1, and also from 1 to positive infinity, and the graph is going to be concave down between -1 and +1.